All right, hey folks, how we doing? Continuing along with this kinetics. So we're gonna get into what I think is some really cool stuff. I think I'm probably saying that at the beginning of every single one of these videos. So I'm gonna get into, on this lecture, pseudo first order reactions, which I'll describe here momentarily. And I think I should have enough time to also talk about equilibrium, as well as temperature based reactions. So reactions affected by temperature. So I'm going to keep my eye on the time, and we'll see how many of these slides I can get through. Okay. So a pseudo first order reaction are really interesting, and this is really practical for how kinetics is actually done in the laboratory. So pseudo means kind of, in the simplest way. So it's kind of a first order reaction, okay? And so what makes this a pseudo first order reaction, I need plenty of room on the slide. So I'm going to start up here, and I'm going to say, suppose that we have a second order reaction, okay? So suppose we have a reaction that's first order in A and first order in B, giving us a true second order reaction. As it turns out, these reactions are pretty difficult to do experimentally, because you'd have to monitor the concentration of both A and B simultaneously. And that can be done. It's not impossible. However, it's difficult. So we can make this what's called a pseudo first order reaction by imposing the following. We can make the initial concentration of B much greater than the initial concentration of A, or provide a steady source of B such that the following. So in either one of these, we either make the initial concentration of B much larger than the initial concentration of A. If that's not feasible, if that's not something we can actually do, then in our reaction we can continually add B. And we can continually add B at a steady rate such that the concentration of B at any time is always roughly equal to the initial concentration. So either scenario gives us this notion that B is not going to change in time. Okay? So if B is much greater than A, if B reacts away, it doesn't really look like much changed. Or, and this is what I think is more realistic, we're providing a steady source of B. We continually refresh the B that was replenished such that B is always at a constant concentration. Okay? And so now what we get out of this thing, so our true second order rate would be K times A times B. So this would be our true second order reaction. Okay? But now, under pseudo first order conditions, this rate is going to be K prime times A. All right, so then I'll write next to that pseudo first order. And we recognize now that K prime, the pseudo first order rate constant, is going to equal the second order rate constant times the initial B concentration. Okay? So in other words, we absorb this B concentration into K, and we get a pseudo first order rate constant. Okay, so I'll say our pseudo first order rate constant is K prime with the appropriate units of 1/seconds, and our second order rate constant is this K right here. All right? And so now what happens under this scenario, okay, if I write now negative dA by dt equals K prime times A. So that's a differential equation that we can solve, right? No doubt. And hopefully you remember from the last discussion, solving the second order rate constant is much more difficult, although it can be done with a program such as Mathematica. But as far as fitting data, and you can see that I've got this data set that I had you fit earlier in the semester. I'm going to come up and talk about that in a moment. When we do pseudo first order, this makes fitting data and determining a rate constant much easier. So for example, when I go to solve this, I would come up with let me make some more room. Oops. So I'll write this under here. So I can say I'm going to put this in relative units. A of time t equals A0 equals now e to the negative k prime t. Okay? And so that would give us a nice exponential first order decay. All right? And what we also notice now is that in this relative units that I've got here, you can start to see this is how we're connecting this, right? If I plot this normalized concentration, then when I fit this an exponential like you did in e to the negative kt, the only fit parameter is the rate constant k. So now what about this x-axis? I didn't put this in time. It's called OH exposure, or just generally exposure. So what does all of that mean? Well, I'll remind you here. Let's expand on this. Okay, A at prime t over A0 equals E. So we said that K prime is K times this B. So let's fill that in. So let's actually go ahead and write this as K times B0 now times T. Okay, well, if we still want to fit this to an appropriate first order rate constant, then what we can actually do is instead of plot this as concentration versus time, okay, instead we can plot this as relative concentration versus exposure. So what is exposure? Well, it's this B0 times T, right? So I'll say this little chunk right here, instead of time, it's what we call exposure. So in other words, it's the duration of time that a reactant is exposed to another reactant. And you notice it has units of seconds, molecules per cubic centimeter. And so that's because the concentration of B would be molecules per cubic centimeter times time in seconds. That gives us the seconds times molecules divided by cubic centimeters. Okay? And so now if I plot this x-axis in this way, okay, where instead of versus time, it's time multiplied by the concentration, then I will get a first order decay out of that. And when I fit this, I get an apparent first order rate constant. Okay? No, excuse me. I'm sorry. I misspoke there. I get the second order rate constant. Okay? Even though it's plotted as a first order, right? We remembered that K, not K prime, K is the true second order rate constant. So I can get the second order rate constant out of this thing by doing this in pseudo first order conditions and plotting it as concentration versus exposure. Okay? So I've run out of room on this slide. So this slide is time constants. We'll also say time constants and methods. So the first thing I'll note is for the time constant, when we say dA by dt equals K prime times A, so this is my, I'm going to do this first order. So if we're just saying first order reaction, right, we know that tau, the lifetime, was 1 over K for first order. Okay. I could also say 2 lifetimes would technically be 2 over K. 3 lifetimes would be 3 over K. So what about now under pseudo first order conditions? When I say negative dA equals K prime times A. So when I'm using a K prime there, I recognize that's the pseudo first order rate constant. So K prime is K times the B initial concentration. Okay? So now I can still use this notion of a lifetime under pseudo first order conditions. Okay? But now instead of it being just 1 over K, it's going to be 1 over the second order K times the initial B concentration for the lifetime. Okay? And so we know that then 2 lifetimes will just be 2 over K times B initial, and so forth. Okay? So now how do we do these experiments? How do we do these exposure experiments? So I'm just going to do this very briefly. Okay, I could spend like a whole lecture on this, but essentially the way that you do one of these exposure experiments, the easiest thing to do is to hold time constant. Okay, so I'm going to say how we do exposure. I just got to erase it. How we do exposure experiments. First thing, hold time constant. So if you're holding time constant, then how do you vary that x-axis? Well, what you can do is use a flow tube. And this can actually be done in the gas phase or liquid phase. I'm going to describe this for the gas phase. But there's a lot of really cool kinetic work coming out with doing these types of flow tube experiments in the liquid phase using perielastic pumps, right? Pumping the reactants as a liquid phase through a constant cell. Okay, so in this flow cell, what ends up happening, I'll draw this like there's these little, places where the reactants can come in and then exit out, okay? So your time, because the flow cell is always the same dimension, if you're using the same flow rates, the time is always constant. Okay, so now what you do is you pump in your reactant A, right, at some initial concentration, okay? And then what's going to come out of the flow tube is A at any time T. And really we recognize because the time is constant, the concentration of A won't change unless we change the concentration of B. Okay? And furthermore, if we recognize that, in this experiment here, this was done through with the OH radical. OH radical is completely unstable. So what we actually did was in our flow tube, we surrounded this flow tube with a bank of UV lamps, and then we put in a precursor to OH radical. And when the OH radical entered this flow tube that was surrounded by UV lamps, then the OH radical is generated at a constant concentration, but only in the flow tube. And you change the X scale by jacking up the OH precursor for each experiment. Okay, so in other words, I will say we introduced some other reactant, C. Okay? And typically, so I'll draw like here, like a little lamp, something like that, right? Okay, we'll say this is like a UV lamp. And what's really cool about this, everything else in the experiment is completely blocked off from light. So we literally wrapped all the tubes and everything else in black cloth. And the only thing we kept exposed to light was the constant volume flow tube, right? So that we know that the time is always constant. And so now we impose some reaction that says like C under UV light makes our reactant B that we're interested in, right? We'll go back to this. The reaction we're really interested in is A plus B goes to products, and we want to impose that B at any time is just constant, okay? So now what we do in an experiment, we flow in this C, but we know C under the UV lamp is really converted into the reactant that we want, okay? And then so how do we know how much B we created? Well, in a separate device, we monitor the remaining C that's left over. So now I know I said previously, well, the whole goal of this is to not have to monitor two reactants at once. Sometimes you have to do it. And the reason why we have to do it is because the OH radical is so reactive, we can't measure it. You can't measure the OH radical. It's too reactive. So then what we do instead is, well, we say that we put in a certain amount of C that won't be consumed. We know what the rate constant, we know what this rate constant is. You know, that's known. So we monitor simultaneously A and C. We often call this species C a tracer or even a precursor. So we can monitor that. So it's typically something stable that we can monitor. Okay. Then the way that we create each one of these data points. So all that I'm describing in one static experiment, all that does is generate like one data point. So then how do we get the time series of data points? Well, in each successive experiment, we just keep increasing the concentration of C, the precursor. We keep the same concentration of A initially, right? And so now in each experiment, we let this run through the flow tube. And by the way, in our experiments, this flow tube, it only took like a minute, you know what I mean, to get through. So it's under this steady state. So if we have a device that can measure concentration in real time, which I won't get into that. It was a really fancy mass spectrometer where we could measure, we didn't have to do any chromatography at all. We could measure concentration in real time. So then now your time is always constant. You're not doing a stopwatch, which is cool. Your instrument is just telling you, you know, any one of these data points. And now when you're ready to move on to the next data point, you increase the precursor. That generates more of B, the reactive species you're interested in, okay? And then your experiment shows you more of A is consumed. And then you keep doing it. You keep increasing the precursor C until you've reacted it all away, right? Because eventually no A will make it out of the flow tube. You will have reacted it all away, which you can see down there. And very conveniently, you can now fit the data in this exposure space. That's what we call the exposure space instead of time space. And you recover your second order rate constant. So it's a really cool experimental method. It's not talked about at all in the book, but it's how we actually do kinetics in the real world. Okay, fantastic. I'm going to move on. And let's talk about equilibrium. So I'm going to close that. This is going to be really our first look at a simple mechanism. Okay, so let's suppose we have a very simple first order equilibrium going, and a good example of this might be something like isomerization. You know, perhaps a cis isomer becoming a trans isomer through time. Okay. So now, and we'll just impose that both of these are first order to make life easier, okay? I don't have any example of this in the Mathematica model, but I did want to just remind you, first order reactions, right? Exponential, as we saw. So what we do is we break up these reactions into two forward reactions. So I'm going to say A goes to B with rate constant K forward, and B goes to A with rate constant K reverse. Okay, and so now this is really important because this is going to be how we start to create a complex mechanism. So when I start to write now the rate of A, I'll write it over here. I'll say dA by dt. And I'm going to absorb the negative sign. We know that we put the negative sign there for A. But I want you to start getting into the habit of recognizing that for the reactant, it's going to be negative K forward times A. Okay, that takes care of our first reaction. So then what about this second reaction? Okay, well, I'll just put this over here in the just on the side. We know that we could write that in terms of B. And we could write that as dB by dt equals K reverse now times B, because it's all about the reactants. Okay? But what we really want to do, and this is what makes it complicated, we want to think of this as a total rate law, a total differential expression. So now I'm going to take advantage of the fact that negative dA by dt equals positive dB by dt, right, from the relative rates. And so now what I can say here, my total dA by dt, it's going to be negative K forward times A plus K reverse times B. So this is my total rate law for this equilibrium expression in terms of A. Okay? And the reason why we're thinking about that in terms of A, because typically we would have B initial equal to 0 and A at any time plus B at any time must equal the initial concentration of A. So all that is saying is stoichiometry, right? If I have, let's say, 1 mole, just like this, right? If I have 1 molar of A, at any time in the reaction, the total concentrations have to add up to 1 molar. We're not making new mass, all right? So, but this is critically important, and we're going to get a lot of experience doing more complicated steps, okay? And I'll show you how we do it when we get to more complicated reactions. So, but for now, what I'm going to say over here, solving this thing becomes complicated, and I'm not going to make you solve it by hand, and I'm not going to solve it by hand. But now we recognize that B will have a differential rate than A because it has a different rate constant. So in other words, K forward and K reverse have different concentration dependencies. So now what we want to do is rewrite this expression in terms of things that are a little bit easier to write, okay? So I can now write, this is plus K reverse, and B at any time, so I'll rearrange this, is just going to be A0 minus A. I'm dropping the subscript T in this because I haven't technically integrated the expression yet, right? And so now, let's see here. If I do a little bit more math, just some algebra, all right, then I will say dA by dt equals negative K forward plus K reverse all times A plus K reverse times A0. And this is put into this form because, as it turns out now, this is a standard first order differential equation. And so we call that a diff-EQ. That's what some folks call differential equations. And it has a standard result. So I'm not going to show you how we solve this. As I've kind of alluded to, solving these differential equations is complicated. So I'm going to give you the solution to this, okay? And the solution becomes A at any time equals, and so this becomes kind of a complicated expression, okay? But it's not so complicated that it's impossible to understand. So K reverse plus K forward times E to the negative K reverse. Oops. Maybe it's just too complicated for me to write it in a clean way. I'm going to write it down right here where I've got more room. Okay, so A at time t. So we'll say solve. Okay. Equals k reverse plus k forward times e to the negative k reverse plus k forward t. Okay? All divided by k reverse plus k forward, all times the A initial concentration. And what I want to point out about this, it looks complicated, but it's just a first order decay. That's all that it is, right? So we recognize our simple first order decay. Let's see if I have one written here somewhere. Yes, we recognize our simple first order k is just e to the negative kt, right? And if I look at this expression, I could rearrange it and say at equals a0 times e to the negative kt. So keep that in your heads, right? Well, now if you look at this, look, at equals a0, so I could divide it out to do that, relative concentration rates. But now look, just k reverse plus k forward divided by k reverse plus k forward, that's just going to end up being a constant, a unitless constant, because the rate constant units will be the same. And they add up, and then you divide them by each other, times e to the negative kt. Even though it's k reverse plus k forward, it still gives us this first order expression, which is cool. Okay? And let's see, moving on here. So first order reactions approaching equilibrium. I'm also not going to do this full derivation. But basically what we can show is if we kind of if we were to spend more time with this and work our way through the math, what we would find is the equilibrium concentration of A can be written as K reverse divided by K reverse plus K forward all times the initial A concentration. Which also makes good sense, okay? Because now we can start playing with this and start talking about things like, well, what happens when K reverse is much, much greater than K forward? Or what happens when K forward is much, much greater than K reverse? And we can arrive at some pretty cool things related to what we already know about equilibrium, okay? And if we were to continue solving this, and now I'll note that this is approximate, because again, it's solving more differential equations which don't have perfect solutions. But what we would get as this approximate result is the equilibrium constant K, as we know, will be the B over A, right? If we're talking about our very simple equilibrium. And as it turns out, this just approximately, and to a very good approximation, just ends up equaling K forward over K reverse, which makes sense when you really think about it, right? When you think about a simple equilibrium, it will be related to the forward reaction over the reverse reaction, because the forward reaction creates B, the reverse reaction creates A, so these are in kinetic competition with each other, right? And once we know with equilibrium, once those concentrations have stopped changing, right? Like now that's stopped changing, and now this has stopped changing. These concentrations are going to give us our equilibrium constant, okay? Now there's a whole bunch more that I wanted to say on what's called relaxation methods, which is what this graph is all about. But I'm only going to talk about this very, very briefly. So this is an experimental way of looking at Le Chatelier's principle. Okay? So this is pretty cool, and this is actually stuff I do in my own research. But what we would see in these relaxation methods, Let me draw this graph here a little bit bigger. Okay. So suppose we're doing some reaction, right? And we're monitoring its progress. You know, maybe we've monitored the reactant and it looks something like this. And we've monitored the product and it looks something like this. And let's suppose we enact a change. We attempt to shift the equilibrium. Perhaps we change the temperature of the reaction, or we add more reactant, or we change the volume, right? A number of things that we could do to perturb this equilibrium, okay? Then what we would observe, depending on how we've perturbed the equilibrium, is another exponential either growth or decay, depending on which way we've shifted the equilibrium, okay? So for example, this is showing you different temperatures, right? And we're going to get into that next. But suppose by increasing the temperature, let's just suppose here, that by increasing the temperature, it favors more reactants, okay? So that means, in other words, maybe we have an endothermic reaction, right? So suppose endothermic. So if I increase the temperature, okay, I'm going to increase the production of B, right? So then now what I would see here is more B getting produced, but it would be another one of these exponential rises, and now we have a new equilibrium amount. And so we would see, let me label this, we'll say that's A and that's B. And so now if we've increased this temperature, right, to shift the equilibrium to producing more B, then more A would be consumed, and correspondingly we would see something like this, okay, right? And now, as you might guess, this would actually increase the value of the rate constant, which is what we would expect for an endothermic reaction as we increase the temperature, all right? Okay, very good. So what I'm going to do now, because that's about a half an hour, the next slide is all about temperature dependence. And I want to make sure that I talk about that plenty with respect to the model right here. Okay, the last model, model 5. Where is it? Yes, temperature dependence. So I'm going to record a new video with this. See you in the next one.